Hello LEGO fans, welcome to LEGO 48. Today I want to talk about spacers. As I mentioned in my video on the GBC standard, balls can arrive in batches of up to 30 at a time. Depending on the design of your GBC module, you may need the balls to be separated so they move through your module at 1-second intervals. And that's what a spacer does for you. You can also link a spacer to a part of your module in order to synchronize ball movement, in which case a spacer then provides timing. Before I show you my spacer designs, I want to talk about two key design issues that I've encountered. The first is what I call push, and the second is what I call random arrival. First, let's talk about push. This occurs when you get a significant buildup of balls in front of the spacer. For instance, if you dump a lot of balls into the hopper in front of the spacer, you'll have a solid column backed up all the way into the hopper. If pressure is applied to the last ball, it can push on that entire column, creating pressure on the ball at the front of the line. Push can manifest in other ways too. It can be the result of simply having a large number of balls stacked up. Yes, they don't weigh much individually, but when you get 8 or 10 of them together, it adds up. It can also occur when balls arrive at speed. For instance, I discovered that my rocker design was susceptible to high-speed balls that would enter the rocker and ride it like a ramp, continuing right over and past the spacer. If I'm relying on the spacer for timing, then these balls are leaving too early, defeating the point of my spacer. Random arrival is the term I use to describe balls that arrive with random timing, and just happen to arrive at exactly the wrong time, causing the spacer to jam. For instance, my original revolving door spacer had this issue. If there wasn't a ball in the spacer and a new one arrived just as the opening went past the infeed wall, a ball could get jammed in there. When I first implemented my closed-loop GBC system, I really thought that random arrival would be a rare problem, and I was kind of surprised when things jammed up more often than expected. But I finally figured out why. It turns out that random arrivals aren't really that random. Let's assume that this circle represents the cycle time of your spacer, and the white triangle represents the arrival time of a ball. The open triangle represents the point in the cycle where the system will jam. If your module is being fed by another one that is feeding balls at approximately 1 ball per second, chances are that the exact frequencies are going to be off a little. If the cycle time of the previous module is a little slower than mine, then the arrival point for each successive ball will be just a little bit later. If the cycle time is faster, then each ball will arrive a little bit earlier in the cycle. If this continues long enough, then the arrival times will continue to shift around the cycle, and while they may not immediately hit the jam point, like a spirograph drawing loops, it will eventually come around and jam. Referring to this problem as random arrival is definitely inaccurate terminology, but I've gotten used to the phrase and now it's kind of stuck. The key is to make sure that we design spacers that will tolerate balls arriving at all points of the cycle. So now let's take a look at some of the designs that I've created. This is one of my first designs. It uses a simple dual gate mechanism that allows one ball through at a time. It works, but it's a little crude, and it will keep making that click-clack noise the entire time it's running. Also, the connection between the gates and their support arms is not very solid, so I doubt that this would hold up for very long before the gates fell off. My next design is this one. It uses rotating blades to do the same thing as the previous design, except the blades move in a circle instead of up and down. You can see how the first gate lets one ball through at a time, because that ball will be stopped by the second gate. By the time the second gate opens, the first gate is closed, so only the one ball can advance. Note, because there are 2 slots in each wheel, the spacer will pass 2 balls per revolution rather than just 1. One of the cool things about this design is that it's bidirectional. In other words, it doesn't matter which direction I turn the input gear, this spacer will work equally well in either direction. Unfortunately, the downsides of the design are 1, it's very awkward to get power to the main axle which is suspended over the track, and 2, it is still susceptible to the random arrival issue. Here I've got a really simple spacer built using 4 knob gears, also known as knob wheels. This one has to really be geared down because it will naturally pass 4 balls per cycle. That is, it will spit out 4 balls for each revolution of the knob wheel. Jamming isn't an issue with this design, but push is. Because there's not a lot of material holding the balls back, if they arrive with any kind of speed or force, they are able to skip right across the top of the knobs. This design uses a piston to lift balls up and over a stop. This design is pretty resistant to push, and there isn't anything for the balls to jam against. It also has the advantage of actually adding height to the balls, which can be helpful if the next part of the module is elevated. Unfortunately, the downside of this design is that it requires a lot of clearance underneath the track, which means the minimum elevation for the input and output tracks is fairly high. Also, when I tried to implement this and connect it to a motor, there's a tendency for the piston to jam against or get caught on the other Lego parts around it, so I just couldn't get it to work reliably. I know it has to be possible to build reliable pistons because there are plenty of other GBC modules based on this design, but I don't know what the secret is. Here's another design that I tried. This one will also pass 4 balls per revolution, but it solves that by using a knob wheel and rotating arm with a pin attached. Every rotation of the arm causes the pin to hit one of the knobs, advancing that wheel by exactly a quarter turn. This allows 1 ball to pass through at a time. Push is not an issue with this design, but random arrival definitely is. This design is extremely prone to jamming, and the height between the rotating bars and track has to be exact, or it can end up letting more than 1 ball through at a time. So then I tried this design. It features a cradle that rocks back and forth, picking up 1 ball at a time, rocking forward to deposit it on the lower exit track, and then returning for the next ball. This is a really nice design that is bidirectional and only passes 1 ball per revolution. It's also fun to watch in action. One of the other things that I like about this design is that it can be made very compact. This is the smallest version that I've built. It's only 11 studs long with an input height of just over 4 rows and an exit height of 2 rows. Unfortunately, while not prone to jamming, it is susceptible to push. If the balls come in too quickly and the rocker arm is at just the right angle and moving away, they can hit the cradle like a ramp and go right over it. If you're trying to use this for precise timing, that can be a problem. One way around that is to add bends to the input track. That bend will slow down the incoming balls so they don't hit the caddy as fast. Finally, this is my favorite design. It has a vertical wheel with notches in it that will fit exactly 1 ball at a time. As the wheel rotates, it carries 1 ball forward in the notch while holding back any other balls. I love the action on this. It's very smooth and it doesn't have any vibration like the reciprocal designs do. And since the wheel is lifting balls up, it won't jam them or suffer from random arrival. Push was a problem with this design, as balls could be lifted up and over the wheel while it was turning and advanced when they weren't supposed to. I solved that problem by adding this arm here mounted on a pin. This provides enough resistance to hold back any balls that aren't in the wheel slot, while also offering enough movement flexibility to prevent jams. This design is obviously not bidirectional, so you have to make sure that the input power is rotating in the correct direction. There are 2 ways of implementing the wheel. There's the butterfly style, which will advance 2 balls per revolution, or you can use this design, which only has a single notch and only advances 1 ball per revolution. Which design to use really depends on the speed of the input power and what you're trying to do with it, but it's nice to have the flexibility. In this case, I'm using the butterfly wheel, but there's a 2-to-1 gear reduction between the input and the wheel, so I'm only advancing 1 ball per complete turn of the hand crank. I hope you found this useful. Have fun building!